Hi, this video is about the hidden language of physics and specifically about how each measurement has three traits with it. So, as I said, in physics, we use a hidden language, and it's not hidden on purpose, it's just hidden if you've never learned physics before. So, let me explain. I like football, and so I like to watch it. And I know some of the lingo with football. I don't really know what most of it means, but you might have heard something like this before if you've ever watched football. Blue 42, set, hut, hike. Right, that might be something that the quarterback calls out before the play starts. Now, that itself is a hidden language. It's hidden on purpose because he's saying some kind of code words, some language that his team knows. He's trying to communicate something to his team, but he's trying to keep it secret from the other team. So, for example, like blue might refer to a certain formation. Four might refer to the player in position four. The number two is maybe a type of play that player is going to do now. Then you get ready and you start the play. That could be the code language behind that sentence in football language. Now, in football, the language is hidden on purpose because you're trying to keep it a secret. But in physics, it's not meant to be a secret. It's just a secret when you don't learn physics, when you haven't learned this before. But I'm here to tell you what the secret is. I'm here to help you understand the mystery of the physics language, and hopefully it'll make things a little bit more clear. So this is an example of a physics sentence here. In blue is the physics sentence, and I added the translation into English all around it. So the blue is physics language, the green is English. And so to read this and just literally read it in physics language, this symbol is delta x equals negative 10.0 centimeters. That's how I'd read that in physics. Now, if I wanted to translate that into English, I have all these other words that kind of go with it. And so the delta I know means the change in. X I know refers to the horizontal position of an object. This little symbol right here tells me that there's a direction involved. That's all stuff that we're going to learn later on. But what I want to focus in on is this last little bit today, and that's the measurement part. So we're going to ignore the rest of this and talk about that in a later part. But today I wanted to talk about what is this last little chunk, the measurement part. So, in physics, each measurement that we make has three traits or characteristics. And we're focusing in on this last little bit of that sentence we saw before, that physics sentence. And I wanted to point out three characteristics or three traits that are included in that measurement. The first is the magnitude. That's a word we use in physics to describe how much. So in this case, the magnitude would be 10, 10.0. It's a magnitude is just the number that's involved in the measurement. The second one is the hidden part that's implied, and it's not spoken out loud. It's just in how you write the number exactly, and where you put the decimal place sometimes matters, and where there are certain zeros in certain places. All of that communicates the precision of the measurement. And the precision really just means how certain we are that that measurement is what we say it is. So if we say the measurement is 10.0 meters, we're kind of giving you giving away how much precision is in that measurement by the 10.0 part. The 0.0 kind of gives you a hint as to, okay, this is a little bit more precise than just 10. So the precision is always included in a physics measurement as well. And the third is the unit. And this is just some known reference point. So in this case, it would be the M, which stands for meters. So those are the three traits of any physics measurement. So let me show you three measurements that look very similar, but they have some differences. So we have 10.0 meters, we have 10 meters, and we have 10 yards. Now, these three measurements are different from one another for a couple of reasons. These first two measurements appear to be identical, and that's where a lot of people might get confused when they look at physics and they think, what are you talking about? They're the same. 10.0 meters, 10 meters, that's the same. The difference is that second trait, that precision element. The 10.0 measurement is more precise than the 10, right? When we say 10.0, we add that extra 0.0 in there to really indicate this measurement is relatively certain. We know it's not 9.9. We know it's not 10.1. We know it's 10.0. Like that's more precise than just 10 meters. Because writing it like this, 10 meters, that's actually not quite certain at all. It could be as low as 9.5. We just round it up. Or it could be up to 10.4. It could definitely be 9.9. We just rounded up to 10. You know, this is not a very precise number. And maybe that's all we could do. Maybe our measurement device is not very precise. We're trying to just use whatever we have around us. And we can't get any more precise than 10 meters, and that's okay. There's nothing wrong with that. The way that we communicate the number matters, though. And so 10 meters is different than 10.0 meters in physics because of the precision. And then over here, this is obviously a different unit. And so that means it's just entirely a different measurement. Even though it's the same magnitude as the other two, 10, it's a different unit. So let's look at two examples of these measurements, some realistic measurements here that you'll come across. Okay, so when you write down any measurement in physics, you must include all three traits of that measurement, or your work will either be misleading or meaningless. And let's look at an example. So for this example over here, a car travels 190 miles in 3.0 hours. Okay, so if I ask you to find the average speed of that car over the 3 hours there, you might be able already to know what to do here. You just take the distance you traveled, 190, and you divide it by 3. So put that in a calculator, 190 divided by 3, you get this, 63.333333 repeating. Okay, so when you go in to write down your answer, you go to tell the teacher, you know, the speed of the car. The measured speed of the car is not 63.33333333 miles per hour. That is not the measured speed of the car, because that implies amazing precision. You're telling me that you measured the car to have an average speed that precisely, 63.33333. It's not 63.33334. It's exactly 63. No. So the honest measurement for this particular problem is the car speed is 63 miles per hour. So you kind of cut off all that extra stuff and you round it to an appropriately precise number. And this, how you decide on how precise you're going to be is based on how precise your original measurements are. Each of these two measurements both add two significant figures, which is a topic for another video. And so because of that, we're going to round this to 63 miles per hour. Now, this other example, let's say you come up with some calculations and you determine that you have a mass of 50. Okay. 50 what? 50 grams, 50 tons, 50 earths. No, a measurement must include a unit. It's meaningless without a unit. So usually we measure mass in kilograms. And so I think this person meant to say, I have a mass of 50 kilograms. Well, that's all I got for you in this video. Remember, how you do anything is how you do everything.